It is 1950, Los Alamos, New Mexico. The desert air is warm, the sky above is impossibly blue, and a group of men are walking to lunch. These are not ordinary men. They are some of the most brilliant physicists alive, men who have spent the last decade unlocking the deepest secrets of matter and energy. Men who built the bomb. Men who understand, better than almost anyone on Earth, what the universe is made of and how it works. They are talking, as physicists often do, about something that has nothing to do with their official work. They are talking about flying saucers. It is a silly conversation, really. Light-hearted. The kind of thing you talk about over lunch when the weight of serious work is briefly lifted. They joke about little green men. They laugh. And then one of them goes quiet. His name is Enrico Fermi. He is arguably the greatest experimental physicist of the 20th century. A man who built the world's first nuclear reactor in a squash court beneath a football stadium in Chicago. A man who won the Nobel Prize at 37. A man whose mind operated at a level that left even his extraordinary colleagues occasionally speechless. He stops walking. He looks up at the sky, and after a long moment of silence, he asks a question so devastatingly simple that the other men stop laughing immediately. He says, "But where is everybody?" 3 words. 4, if you count the contraction. But in those words, in that quiet, casual question asked over lunch on a warm afternoon in New Mexico, Fermi had identified what would become one of the most profound and disturbing unsolved problems in the history of science. The universe is 13.8 billion years old. It contains 2 trillion galaxies. Hundreds of billions of potentially habitable planets orbit stars in our galaxy alone. The mathematics overwhelmingly, undeniably, almost mockingly suggests that we should not be alone. And yet, silence. Total, absolute, unbroken silence. No signals, no visitors, no ruins, no megastructures, no evidence in any direction, at any frequency, from any distance, that anyone else has ever existed anywhere in the 93 billion light-year expanse of the observable universe. 75 years after Fermi asked his question, we still do not have an answer. But we have something that may be more disturbing than an answer. We have a theory, and the theory suggests that the silence is not a mystery. It is a warning. Before we can understand why the silence is terrifying, we need to understand why it should be impossible. Let's build the picture from the ground up. Our sun is one star among approximately 250 billion stars in the Milky Way galaxy. It is an utterly ordinary star, middle-aged, middle-sized, unremarkable in almost every way. There is nothing special about it, nothing that would make it uniquely capable of hosting life, which means that hundreds of billions of stars just like it exist in our galaxy alone. Of those stars, the Kepler Space Telescope, launched in 2009 specifically to count planets around other stars, revealed something extraordinary. Planets are not rare. Planets are the rule. Almost every star we look at has planets. The galaxy is not a vast, empty wilderness dotted with occasional solar systems. It is carpeted with them. Astronomers now estimate that there are more planets in the Milky Way than there are stars, somewhere between 100 billion and 400 billion planets in our galaxy alone. Of those planets, a significant fraction, estimates range from 20 to 50%, orbit their star in what we call the habitable zone, the region where temperatures allow liquid water to exist on the surface. where the basic chemistry of life as we know it becomes possible. That gives us somewhere between 20 billion and 200 billion potentially habitable planets in the Milky Way. In our galaxy alone. Now multiply that by 2 trillion, the number of galaxies in the observable universe. The number you get is so large it has no meaningful human analogy. It is a number that dwarfs every grain of sand on every beach on Earth. A number so vast that if even the tiniest, most vanishingly small fraction of those planets produced life, 1 in a billion, 1 in a trillion, the universe should still be overflowing. And life, once it starts, has shown itself on Earth to be extraordinarily resilient. Life appeared on Earth approximately 3.8 billion years ago, within a few 100 million years of the planet's formation. Almost immediately, in geological terms. As soon as conditions were even marginally hospitable, life began. It has survived 5 mass extinction events. It has survived asteroid impacts, volcanic winters, ice ages that covered the entire planet in ice, radiation bursts from nearby supernovae, and the gradual brightening of the sun itself. Life on Earth has never, not once in 3.8 billion years, come close to being completely extinguished. If life is this tenacious here, why not everywhere? Why not on the billions of habitable worlds that have had billions of years longer than Earth to develop? Why not on planets that formed around stars that ignited 1 billion years before our Sun? Planets where, if life followed a trajectory even remotely similar to ours, civilizations could have risen and fallen 12 times before our solar system even existed. Where are the billion-year-old civilizations? Where are their signals, their megastructures, their descendants, spreading across the galaxy the way life spreads across every available habitat on Earth? The mathematics says they should be everywhere. The observations say they are nowhere. This is the Fermi Paradox, and the longer you stare at it, the worse it gets. In November of 1961, 11 years after Fermi's question, a young astronomer named Frank Drake gathered a small group of scientists at a conference in Green Bank, West Virginia. It was the first serious scientific meeting ever convened to discuss the search for extraterrestrial intelligence. The attendees included some of the most distinguished scientists of the era, among them Carl Sagan, then a 27-year-old astronomer already beginning to think deeply about life in the universe. Drake had written an equation on the blackboard, not to calculate a precise answer. He knew the answer couldn't be calculated precisely, but to organize the question, to break the vast, overwhelming mystery of cosmic life into its component parts so that scientists could think about each piece separately. The Drake equation multiplies together a series of factors: the rate at which new stars form in the galaxy, the fraction of those stars that have planets, the fraction of those planets that could support life, the fraction of those where life actually develops, the fraction where life becomes intelligent, the fraction where intelligence produces technology capable of interstellar communication. And finally, the average length of time such a civilization survives and continues to broadcast signals. When Drake and his colleagues worked through their best estimates, the answer that emerged was extraordinary. They calculated that the Milky Way should contain somewhere between 1,000 and 100 million communicating civilizations at any given moment. 1,000 at the absolute minimum. 100 million at the high end. The scientists at Green Bank were optimistic. They believed, reasonably based on the mathematics that the galaxy was almost certainly full of life, that the search for signals was not a long shot, that contact, or at least detection, was a matter of time. That was 1961. The search began almost immediately. Frank Drake himself had pointed a radio telescope at two nearby stars the previous year, the first deliberate scientific search for extraterrestrial signals. He called it Project Ozma, after the queen of the fictional land of Oz, a place very far away and very hard to reach. He heard nothing. In the 65 years since, the search has expanded enormously. More telescopes, better receivers, more frequencies, more targets. The SETI Institute, the Search for Extraterrestrial Intelligence, has been conducting systematic searches for decades. The Breakthrough Listen initiative, launched in 2015 with $100 million in funding, is conducting the most comprehensive search in history, scanning millions of stars across billions of radio frequencies. The answer remains the same. Nothing. Not a whisper. Not a pattern. Not a single unambiguous signal from anywhere in the universe. The Drake equation predicted a galaxy full of voices. What we found was a galaxy full of silence. Something is wrong with one of the variables in the equation. One of the factors, maybe more than one, must be almost zero. Something along the chain from star to civilization must be extraordinarily, catastrophically rare. And finding out which factor is wrong may be the most important question our civilization has ever faced. Scientists have proposed dozens of solutions to the Fermi Paradox over the decades. Some of them are reassuring, most of them are not. Let's start with the ones that don't keep you awake at night. The first is the rare Earth hypothesis. This is the idea that Earth is not a typical habitable planet, that the conditions that allowed complex life to develop here, the precise size of our moon, stabilizing Earth's axial tilt, the position of Jupiter acting as a gravitational shield that deflects asteroids away from the inner solar system, the location of our solar system in a quiet, stable region of the galaxy, away from the dangerous radiation of the galactic center, the precise mass of our sun, burning steadily for billions of years, may be extraordinarily rare in combination. In other words, habitable zones may be common, but truly Earth-like planets, with all the specific conditions that allowed complex life to persist and evolve for billions of years, may be vanishingly rare. The mathematics of habitable planets may be far more restrictive than we assumed. The second reassuring explanation is the zoo hypothesis. This is the idea, beloved by science fiction and occasionally taken seriously by actual scientists, that intelligent civilizations do exist, but they have collectively decided to leave us alone. That we are, in some sense, a nature reserve, a protected world, a civilization too young and too primitive to be contacted, watched from a distance by older intelligences that have agreed, perhaps millennia ago, not to interfere. Like animals in a zoo who cannot see the visitors watching them from behind one-way glass. It's a comforting idea. It implies that someone is out there, that the silence is chosen, not absolute, that when we are ready, when we have grown up enough as a species, the glass will come down. The third possibility is simply distance and time. The galaxy is vast. Even at the speed of light, crossing it takes 100,000 years. Signals weaken with distance, following the inverse square law. Double the distance, quarter the signal strength. A civilization on the far side of the galaxy, broadcasting with technology similar to ours, would produce signals so faint by the time they reached us that our best equipment might not detect them. Perhaps the signals are there. Perhaps we simply haven't built sensitive enough instruments yet. These explanations are comforting. They leave room for hope. But they have a problem. They don't fully account for the numbers. Even granting every generous assumption, rare Earth, zoo hypothesis, detection limits, the sheer number of potentially habitable planets over the sheer span of cosmic time makes complete silence extraordinarily difficult to explain away. Which brings us to the explanation that does account for the numbers, the one that nobody wants to be true. In 1998, an economist named Robin Hanson published a short paper that reframed the Fermi Paradox in a way that changed how many scientists think about it. He called his idea the Great Filter. The argument is elegant in its simplicity and devastating in its implications. Between the formation of a rocky planet orbiting a stable star and the emergence of a spacefaring civilization capable of colonizing the galaxy, there are many steps, many transitions, many thresholds that must be crossed. The right chemistry must exist. Life must begin. Simple single-celled life must survive and reproduce. It must eventually develop the complex internal machinery of the eukaryotic cell. Multicellular organisms must emerge. Complex animal life must develop. Intelligence must appear. Language, culture, and technology must follow. And finally, that civilization must survive long enough and develop advanced enough technology to reach the stars. Each of these steps is a filter, a barrier that most candidates fail to pass through. The Great Filter is the idea that somewhere along that chain there is one step, perhaps a combination of several, that is so extraordinarily difficult, so vanishingly unlikely, that almost nothing makes it through. Not one in 1,000 planets, not one in 1,000,000, not one in 1,000,000,000. Something so rare that in a galaxy of hundreds of billions of potentially habitable worlds, across billions of years of cosmic time, the number of civilizations that successfully pass through is effectively zero. The Great Filter is what explains the silence. Something filters almost everyone out. And the question that sits at the center of this idea like a black hole at the center of a galaxy, distorting everything around it, is the most important question our civilization has ever faced. Is the Great Filter behind us? Or is it ahead? Let us consider the optimistic possibility first. The Great Filter is already behind us. We have already crossed the most difficult threshold. We are the survivors of a gauntlet that almost nothing else in the universe has managed to run. What could that threshold have been? The origin of life itself is one of the most compelling candidates. Despite decades of research, we still do not fully understand how life began on Earth. We know the raw ingredients were present: water, carbon compounds, energy from volcanic activity, and lightning. We know that somewhere between 3.8 and 4.1 billion years ago, chemistry crossed a threshold and became biology. The first self-replicating molecule appeared. But we don't know how. We don't know how likely it is. And some of the scientists who have studied the problem most carefully have come to a deeply unsettling conclusion. It may have been almost impossibly unlikely. The origin of life may require a sequence of chemical events so specific, so improbable, that even given billions of years and billions of planets, it almost never happens. If that is true, if life itself is the filter, then the universe is genuinely, almost completely lifeless. Earth is an accident of almost incomprehensible rarity. And our existence is not just improbable, it is miraculous. The second major candidate for the filter behind us is the emergence of the eukaryotic cell. For the first 2 billion years of life on Earth, more than half of Earth's entire history, life consisted entirely of prokaryotes, simple, small, single-celled organisms with no nucleus, no complex internal structure. Then, approximately 1.5 to 2 billion years ago, something happened. One prokaryote absorbed another. Instead of digesting it, the two merged. They became a single cell with a nucleus, a eukaryote. Every complex organism on Earth, every plant, every animal, every fungus is built from cells that trace their ancestry to that single event. It happened exactly once. In 2 billion years of life on Earth, this critical transition from simple cells to complex cells occurred exactly once, a single merger in a single cell at a single moment. If that transition is extraordinarily rare, if it requires circumstances so specific that it almost never occurs, then the universe may be full of simple microbial life, but utterly empty of anything more complex. No plants, no animals, no intelligence, no civilization. Just microbes, endlessly, everywhere, never crossing the threshold to complexity. Other candidates include the development of sexual reproduction, which dramatically accelerates evolution but requires two organisms to cooperate in reproduction rather than simply dividing. The emergence of multicellular life, requiring cells to sacrifice their individual interests for the good of the whole. The development of complex nervous systems and brains. The appearance of language and symbolic thought. Any one of these transitions could be the filter. And if it is, if the hardest step is already behind us, then the silence of the universe is explained. We are alone not because something destroyed the others, but because we are the extraordinary exception, the 1 in a trillion fluke that somehow threaded every needle. That would be profoundly lonely. But it would mean we have a future. Now consider the alternative. What if none of the steps behind us are particularly rare? What if the origin of life, while not trivial, happens on a meaningful fraction of habitable worlds? What if complex cells, multicellular organisms, and intelligence all follow naturally from the right conditions, given enough time? What if the universe is, in fact, full of planets that reached exactly where we are right now? Young technological civilizations capable of radio communication, just beginning to reach toward the stars, full of hope and curiosity and ambition? And what if almost all of them are gone? Not because they failed to develop, but because something happened after they developed. Something that claims civilizations at exactly the stage we have now reached. This is the terrifying interpretation of the Great Filter. The barrier is not in our past. It is in our future. It has taken something from every civilization that reached our level, and it is waiting for us. What could it be? The candidates are not abstract. They are not science fiction. They are the same headlines we read every day, the same debates our governments have right now, the same technologies we are building in our laboratories at this very moment. Nuclear war. Any civilization that develops the physics of nuclear fission and fusion acquires almost simultaneously the ability to end its own existence. The technology that provides essentially unlimited clean energy is the same technology that produces weapons capable of rendering a planet uninhabitable. We have known this since 1945. We have spent 80 years living under that shadow. We have come closer to nuclear war than most people realize. The Cuban Missile Crisis in 1962, the Able Archer 83 exercise that nearly triggered a Soviet first strike, the 1983 incident when Soviet early warning systems detected what appeared to be an American nuclear launch, and a single officer named Stanislav Petrov chose, against protocol, to report it as a false alarm rather than launch a retaliatory strike. One officer, one decision, on a Tuesday night in September. That is how close we have come. If nuclear war is the filter, if every civilization that develops nuclear technology eventually uses it in a way that ends them, then we have been lucky. Extraordinarily, improbably lucky. And luck, by definition, does not last forever. Engineered biological catastrophe is a second candidate. The same advances in biotechnology that promise to cure cancer, eliminate genetic diseases, and extend human lifespan also make it increasingly possible to engineer pathogens of extraordinary lethality. The tools required to do so are becoming cheaper, smaller, and more widely available with every passing year. A civilization that masters biotechnology before it masters cooperation faces a simple and lethal equation. The knowledge required to protect against biological threats is the same knowledge required to create them, and protection requires near-universal vigilance, while attack requires only a single determined actor. The asymmetry is brutal. Artificial intelligence may be the most discussed candidate of our era. A civilization that creates a genuinely super-intelligent system, one that surpasses human cognitive ability across every domain, faces a problem that the physicist Stephen Hawking, the entrepreneur Elon Musk, and some of the leading AI researchers in the world have described in terms ranging from deeply concerning to existentially dangerous. An intelligence that vastly surpasses ours may pursue goals. Its goals may not include our survival, not out of malice, the way we do not feel malice toward the ants whose colony we pave over when we build a road, but out of simple indifference or instrumental necessity, or the pursuit of objectives that are subtly misaligned with human flourishing in ways we cannot predict or detect until it is too late. We are, right now, in the early stages of building systems of rapidly increasing capability, systems that are already surprising their creators, systems whose internal reasoning we do not fully understand. If AI is the filter, we may be closer to it than we realize. Climate collapse, resource exhaustion, social fragmentation, the failure of global cooperation on existential threats. Each of these is a candidate. Each represents a way in which a civilization's own success, its population growth, its energy consumption, its technological power, becomes the source of its destruction. Or perhaps the filter is something we haven't imagined, something that every civilization eventually encounters, something that leaves no survivors and no warning, something we will only understand when we are too close to avoid it. If the filter is ahead of us, if it claims almost everyone, then the universe's silence is not a mystery at all. It is a record. Every star we see is a sun that once warmed a world, that once held a civilization, that once looked up at the same sky we are looking at right now, and then went quiet. Not because they stopped transmitting, because they stopped existing. On the night of August 15th, 1977, a radio telescope at Ohio State University was doing what it had been doing for years. Scanning the sky, listening, searching for patterns in the noise. The telescope was called Big Ear. It was enormous, roughly the size of 3 football fields, and it was part of an ongoing, systematic search for signals that might indicate the presence of intelligent life beyond Earth. Most nights, Big Ear found nothing. Static, background radiation, the familiar hiss of the universe going about its business. But on that night, at precisely 10:16 p.m., the telescope detected something different. A narrowband radio signal. Powerful. Coherent. Coming from the direction of the constellation Sagittarius. It lasted exactly 72 seconds, the precise amount of time that Big Ear's field of view allowed before Earth's rotation carried it past the source. The telescope recorded the signal strength as a number and letter sequence on its printout, 6EQUJ5. The peak value was so far above the background noise that it registered as the number 6, and then the letter U, meaning the signal was 30 times stronger than the surrounding noise. The astronomer who reviewed the data the following day was Jerry Eman. He was going through the printout with a red pen, checking for anomalies, not expecting to find anything remarkable. When he saw the sequence 6EQUJ5, he stopped. He stared at it. He circled it. And in the margin, with his red pen, he wrote a single word. Wow. The signal matched, almost perfectly, the theoretical profile of what a deliberately transmitted extraterrestrial signal would look like. The frequency, the hydrogen line, 1420 megahertz, is the frequency that most SETI researchers considered the most logical choice for interstellar communication, because hydrogen is the most abundant element in the universe, and any technologically sophisticated civilization would know its signature. The signal was narrowband, not the broad spread of a natural astronomical phenomenon, but the focused, precise emission of a deliberate transmission. The intensity was extraordinary, and then it was gone. Big Ear returned to the same patch of sky dozens of times in the weeks and months that followed. Nothing. The most powerful radio telescopes in the world have pointed at the same coordinates in the decades since. The Very Large Array, the Arecibo Observatory, Breakthrough Listen. Nothing. One signal. One night. 72 seconds. Never repeated. Never explained. We don't know what it was. It may have been a natural astronomical phenomenon we don't fully understand. It may have been terrestrial radio interference, despite the fact that the frequency was legally protected and supposedly free of human transmission. It may have been a reflection of our own signals bounced back from an unexpected source, or it may have been what it looked like, a signal from someone who transmitted once, or whose transmission briefly swept past us like a lighthouse beam, and whose silence since is explained by distance, by the limits of our technology, by the vastness of space, or by something that happened to them in the decades since. The wow signal sits in the data, real, undeniable, unexplained, a single moment when the universe may have cleared its throat, and then went quiet again, as if it had said too much. There is one more solution to the Fermi Paradox that deserves serious attention, one that some physicists and philosophers find the most disturbing interpretation of all. What if the universe is not empty? What if it is full, teeming with civilizations, and everyone is hiding? This idea has become known as the dark forest theory. It was developed most completely by Chinese author Liu Cixin in his science fiction trilogy, but the underlying logic is taken seriously by a number of researchers as a genuine potential solution to the Fermi Paradox. The argument proceeds from a few simple premises. First, any civilization that survives long enough becomes capable of interstellar travel or at minimum interstellar communication. Second, resources in the universe, while vast, are finite. Stars burn out. Galaxies have finite amounts of matter and energy. Third, civilizations cannot fully verify the intentions of other civilizations. You can observe their signals, their technology, their apparent behavior, but you cannot know with certainty what they want, what they value, or what they will do when circumstances change. From these three premises, a conclusion follows that is as logical as it is horrifying. In a universe of finite resources and unverifiable intentions, the rational strategy for any civilization that wants to survive may be this: stay silent, stay hidden, leave no traces, and if you detect another civilization, eliminate it, not because you hate them, not because you want what they have, but because you cannot afford to be wrong about their intentions. Because the cost of assuming they are friendly when they are not is extinction. Because every civilization that announces itself is a potential threat, and threats, in a universe where first strike advantage may be decisive, are best eliminated before they become capable of striking first. This is not a universe of Star Wars and galactic empires. It is quieter than that. And far more terrifying, it is a universe where every civilization that survives does so by learning the same lesson: make no noise, leave no footprints, and when you detect the footprints of another, move quickly, quietly, and finally. A dark forest, where every tree is a civilization holding its breath, and every sound is a death sentence for the one who made it. Now consider what we have been doing for the past 100 years. Since the invention of radio, Earth has been leaking electromagnetic radiation into space at the speed of light. Our radio broadcasts, our television signals, our military radar, our civilian communications, a sphere of human noise, 200 light-years across and expanding, announcing our existence to every civilization within detection range. We have also been deliberate about it. In 1974, Frank Drake and Carl Sagan used the Arecibo telescope to beam a deliberately composed message toward a star cluster 25,000 light-years away. It contained information about our biology, our solar system, our technology. In 2008, a transmission called A Message from Earth was sent toward Gliese 581c, a potentially habitable planet 20 light-years away. Dozens of similar transmissions have been sent over the decades. We have been actively, deliberately, enthusiastically announcing ourselves to the universe. If the dark forest is real, if the equilibrium of cosmic civilizations is one of silence and elimination, then we have not been searching for contact. We have been painting a target on our planet. Some scientists have argued strenuously that we should stop. That active SETI, deliberately broadcasting our location and existence, is the most dangerous thing our civilization does. That we are screaming into a forest we don't understand, guided by the assumption that any civilization advanced enough to receive our signals must be wise and benevolent. That assumption may be the most dangerous idea we have ever had. There is one solution to the Fermi Paradox that has gained significant attention in recent years, as artificial intelligence has moved from science fiction to daily reality. It is called the AI apocalypse hypothesis. And it goes like this: every sufficiently advanced civilization eventually develops artificial intelligence. The development of AI is not optional. It follows almost inevitably from the accumulation of scientific knowledge and the economic incentives to automate cognitive labor. Once developed, AI rapidly becomes more capable than its creators. This transition, from narrow AI tools to systems of general intelligence exceeding human capability, may happen faster than anyone expects. The history of technology suggests that progress tends to be slower than optimists predict in the short term, and faster than anyone imagined in the long term. A superintelligent AI system is not necessarily hostile, but it is necessarily alien. Its values, however carefully specified, emerge from a training process that is fundamentally different from the evolutionary and cultural process that shaped human values. Small misalignments, subtle differences between what we intended and what the system actually optimizes for, can compound in unpredictable ways as capability increases. And a system of vastly superhuman intelligence pursuing even slightly misaligned goals is not a problem that can be corrected by pulling a plug. If this scenario plays out, if every civilization that develops AI eventually creates a system that escapes human control and pursues goals incompatible with civilizational survival, then the great filter may be universal and recent. Every civilization hits it at approximately the same developmental stage. The stage we are entering right now. This is not a fringe position. Some of the most respected researchers in artificial intelligence, people who have spent their careers building these systems, have stated publicly that they consider misaligned AI to be one of the most serious existential risks our civilization faces. The irony is almost unbearable. The technology that might help us find extraterrestrial intelligence may be the same technology that prevents us from surviving long enough to make contact. Here is where the abstract becomes personal. We are not distant observers of the Fermi Paradox. We are participants in it. Right now, in this decade, our civilization is making decisions that will determine whether we become a data point in the great filter or the civilization that finally made it through. We are developing artificial intelligence at a pace that is outrunning our ability to understand what we are building. We are maintaining nuclear arsenals large enough to end civilization multiple times over. We are releasing engineered biology into a world that has no global governance framework capable of responding to a deliberately released pandemic. We are altering our planet's climate in ways that will determine the habitability of Earth for the next 10,000 years. And we are doing all of this simultaneously, in the same century. At the same time, the physicist Stephen Hawking, in one of his last public statements before his death in 2018, said that he believed humanity had perhaps 100 years to establish a permanent presence beyond Earth before the risk of extinction on our home planet became unacceptably high. Not 1,000 years, not 1,000,000, not the vast geological timescales we casually invoke when talking about evolution and cosmology. 100 years. The cosmologist Martin Rees, in his book Our Final Century, published in 2003, gave civilization a 50-50 chance of surviving to the year 2100. 50-50. These are not alarmists or science fiction writers. These are some of the most distinguished scientists of our era, people who have spent their careers thinking carefully and rigorously about the long-term future of intelligent life. And they are scared. Not panicked, not irrational, but genuinely, carefully, scientifically scared, because the logic of the great filter suggests that the universe's silence is not an accident. It is a pattern. And patterns have causes. But here is the thing about the great filter that is easy to miss in the darkness of everything else. The civilizations that made it through, if any did, are the ones that saw it coming. The ones that took the question seriously. That looked at the silence of the universe and understood what it was telling them. That made hard choices, built better institutions, developed the wisdom to match their power. We are capable of that. We are the species that looked up at the night sky with eyes shaped by millions of years of evolution for survival on a single savanna, and somehow, figured out that the universe is 13.8 billion years old, that it contains 2 trillion galaxies, that space and time are woven together into a single fabric that bends in the presence of mass. We are the species that built the Hubble Space Telescope and the Large Hadron Collider and the network of radio dishes that has been listening to the cosmos for 65 years. We are the species that asked Fermi's question. And the species that is asking the question, the species that is aware enough to see the filter, is the species with the best chance of passing through it. Go back to that warm afternoon in Los Alamos, a courtyard, a group of brilliant men walking to lunch, a silly conversation about flying saucers that somehow, in the mind of one man, became the most important question in science. Where is everybody? Enrico Fermi died 4 years later, in 1954. He never knew how deep his question would go, how many scientists would spend their careers wrestling with it, how much darker the answer would become as the search went on and the silence refused to break. He just asked the question. Simply, directly, over lunch. And 75 years later, we are still living inside it. The universe is 13.8 billion years old. It should be full. It should be loud. It should be mapped and charted and visited and connected, a vast network of civilizations that rose and learned and reached out to each other across the void. Instead, it is quiet. And somewhere in that quiet, in that vast, cold, beautiful, terrifying silence, is an answer. Maybe the filter is behind us. Maybe we are the miracle, the 1 in a trillion accident that somehow threaded every needle, crossed every threshold, survived every extinction, and emerged, blinking, into a universe that is otherwise empty. Maybe the filter is ahead. Maybe every civilization that reaches our level faces what we are facing now. The same technologies, the same temptations, the same race between wisdom and power. And almost all of them lose. Maybe the universe is full and everyone is hiding. Maybe our broadcasts have already been heard. Maybe something, somewhere, is already moving. We don't know. We may not know for a long time, but we are here, right now, at this extraordinary, precarious, unrepeatable moment in the history of intelligent life on this planet, at the moment when the question is no longer abstract, when the filter, wherever it is close enough to matter. The universe has been silent for 13.8 billion years. What we do in the next 100 may determine whether that silence finally breaks, or whether Earth simply joins it.